Just spacebar.
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 Yeah, I find them challenging as well. So hopefully this could be a learning experience for us all. Thanks very much, Brian, and thanks for organising this particular event. I think it's going to be a very interesting and useful opportunity for us all to look at the solutions that we need that are coming from technology. So what I'm going to do is give you hopefully a short presentation on some of the messages from science. This is based on as Brian said, the 5th assessment report from the IPCC, which was just finalised at the start of this month. It was published at on the 2nd of November, if I recall correctly. I'll give you the key messages at the start, just in case you lose interest during the presentation. The messages are from the IPCC that human influence on the climate system is clear. The more we disrupt our climate, the more we risk severe, pervasive and irreversible impacts. We have the means to limit climate change and build a more prosperous, sustainable future, and technologies are central to the required transformation. I'll just start off a bit nerdy for those of you who enjoy science, because it's all about energy. And really, what is happening is we're trapping more energy in our climate system. That graph sums up what's happened in terms of how we're trapping that energy, really since the beginning of the Industrial Revolution. And it's measured in watts per square meter. So we're trapping a lot of watts per square meter. You can see on the top bars, the red ones, those are the warming impacts, and you see CO2, carbon dioxide, is the most important greenhouse gas. It's trapping most of those energies. We also have the other greenhouse gases which we're familiar with, such as methane, N2O, and the industrial gases. Tropospheric ozone is also an important greenhouse gas, but it's only got an atmospheric lifetime of a few days. And then we have other factors which influence the albedo, say land use change. And then we have the other pollutants which have a cooling effect. Those are the blue bars at the bottom, and they are sulfates, nitrates in the atmosphere that reflect back sunlight, so the sunlight doesn't get absorbed, it doesn't get a chance to heat up our system. They also impact on the clouds and changing cloud structures. And you can see at the bottom, the yellow bar is the total. When you add them all up, there's a lot of uncertainty in terms of the totality of the radiative forcing. But that's mainly due because understanding the cooling effects is quite complex. It's really complex how clouds interact, particularly when you're looking at over centuries. So total radiative forcing is about 2.3 watts per meter squared. That's an additional forcing, heating per meter across the planet. And where does that energy go, I suppose? 90% of that energy is being taken up by the oceans. You can see it in this chart here, which shows the blue bars are the upper ocean and the deeper ocean. So the ocean is actually acting as we're heating up a hot water bottle. So the oceans keep the planet warm, and we'll be transferring that heat around the planet, causing all sorts of changes. And if you look at the unit of energy at the side there, you're calling zetajoules. Now, even the bankers don't get into the zeta zone yet. That's 10 to 21 joules. So that is a massive amount of energy being taken up by our oceans, and it's increasing. The other areas of use are ice melt taken up in land as well. How is that manifested? We are seeing major changes all over the planet. Some of these changes are unprecedented for decades to millennia. The surface temperatures increased by almost 1 degree since the 1980s. Ice covers reduced, sea level has risen. There's changes in rainfall patterns, and there's been adverse impacts on water resources. The natural world is getting most of these. You've got a lot of shifting of species, moving from hotter to colder areas, and some extinctions have already been occurred due to climate change. And food production has already been negatively impacted with reduced yields of maize and wheat. And there has been some positive impacts in terms of some crops in more northern latitudes. And you can see the sea level rise. The global temperature graph is very, I suppose, noisy. But if you look at the sort of sea level rise, the second chart there, you can see that's very linear in terms of the thermal expansion due to the excess energy that's been absorbed by the oceans. What's causing this? I suppose greenhouse gases. And we can see the trend in emissions since the 1970s there. And unfortunately, that trend is increasing. It was about 1.3% per annum. It's increased in the last decade to 2.2% per annum. And that's primarily CO2, again, largely from using fossil energy. Unfortunately, what has happened that the trend in decarbonisation that did occur over recent decades has been reversed, and you're getting the increasing use of coal as a form of energy again. Even here in Ireland, it's crawled back in again into our energy system. So that is really a difficulty that has to be overcome. As I say, the main source of emissions are energy sector. Agriculture, again, is a key source. Agriculture, forestry and other land uses, industry 21%, transport and the building sector. So that's in 2010, that's a global breakdown of emissions. If we look at CO2 in particular, CO2 is, as I said, the most important greenhouse gas. Basically, it's fossil fuel. Bad land management, cutting down forests, is a major source as well, but we can see that source has sort of stabilised and can be seen to decrease. Overall, the projections are that source from land use will go to zero, even in business as usual scenarios, into the future because of improved land management. And once we pass the population peak, which is anticipated in 2050, it should turn into a net sink for CO2. Of course, agriculture, then you have productions of other gases, methane and N2O. So the impacts are already happening. They're evident from the tropics to the poles on all continents and in all oceans. They're affecting rich and poor countries. We saw the US getting battered there recently, and we're very familiar with what's happening in some of the poorer countries. Future climate. The oceans will continue to warm during this century. That means sea level rise will continue during this century. And even if we stop emitting greenhouse gases, sea level rise will continue on even if we stabilise the temperature. And that has major implications for our coastal cities and coastal assets. It's very likely that the Arctic sea ice cover will continue to shrink and as the mean temperature increases, and glacier volumes will decrease. As I said, food production is already threatened, so what we're showing there, the orange bars show the sort of decrease in food yield, while the blue bars, there are some increases. So obviously the balance is wrong, because the orange bars, the brown bars increase as we get towards the latter half of this century, if we go in a high trajectory emissions pathway. So the impacts are across all sectors in terms of food and water shortages. People will be displaced increasingly, especially in low-lying, vulnerable areas. There'll be increased poverty, coastal zone flooding. And I suppose what we're doing right now in terms of the political sphere, and we know we're getting onto that next, is we have a choice. There's two possible pathways for our future climate. And what I'm showing you there is, I suppose, they're known as RCPs, representative concentration pathways. And by the way, the numbers there are actually the watts per square metre that we'll end up. You might remember I said it's about 2.3 watts per square metre that we're talking about right now. RCP 2.6 is 2.6 watts per square metre that if we stay to that amount of energy, we will possibly stay below 2 degrees global temperature increase. The upper one is the RCP 8.5, and that's our business as usual. That's our current trajectory. That's where we're heading if we don't change our emissions pathways. Even on the low emissions scenario, you're talking about an extra 25 to 55 centimetres of sea level rise by the end of this century, which has implications for a lot of our colleagues from Cork at least, and in Dublin here as well. In terms of what that requires in terms of emissions, the IPCC has looked at a very large range of emission scenarios. I suppose this brownish bar with the is the business as usual scenario, where we end up at greater than 1,000 parts per million CO2 equivalent in the atmosphere at the end of the century. The blue line at the bottom is the 2 degree, and what you should notice there is that requires negative emissions. We will need negative emissions of carbon dioxide before this end of this century if we are to stay below 2 degrees temperature increase. And how negative we go is the question. The other gases, well, the amount of space we leave for CO2, the amount of space we need for the other gases linked to food production, say methane for rice production or N2O for fertilizer use, there will be residual emissions of those gases, but so we'll have to leave more negative space if we want to continue on at adequate levels of food production. And I suppose the negative emissions, as I said, even in business as usual, land use will give us negative emissions. So we have to expedite our land use management to ensure that those CO2 emissions go negative. This is quite a dense chart. I just want to show you the key reasons for concern are those straight line reddish bars, and basically they are unique and threatened systems, extreme weather events, distributed impacts, which are largely economic impacts. Global aggregate impacts are the economic impacts. Distribution of impacts is just the inequity between how those impacts are distributed. And large-scale singular events, which would be the loss of the Greenland ice shelf, which would give us 5 to 6 meters of sea level rise. The chart on the right then is just showing the emission scenario, and really what the IPCC has shown is the global temperature is effectively one-to-one linked to emissions of carbon dioxide. And the black spot shows where we are in terms of current emissions, and the blue diagrams show future emissions. So the more we emit to the atmosphere, the more we are committed. And the key thing about carbon dioxide is once it's up in the atmosphere, it's effectively there forever, or a large proportion of it is. So in order to stay below 2 degrees, the IPCC has given us a total carbon budget of 790 gigatons of carbon. And the amount used to date is about I suppose 60% of that has already been used in terms of CO2 emissions or CO2 equivalent emissions. So the challenge is then, how do we shift around that emissions trajectory? How do we keep the limit below 2 degrees increase, which globally we've agreed under the UN Framework Convention of Climate Change that we should do to prevent the worst and most severe impacts. There are options. We have to do a combination of adaptation with sustained reductions in emissions. It does present significant challenges, technological challenges, and institutional challenges, including for businesses and other institutions. But delaying mitigation will actually increase the costs and increase the challenges associated with taking action. Key options are more efficient energy use, moving to low carbon and no carbon technologies, as Fionn will be talking about later, or others will be talking about. We have to improve food production and carbon sinks, as I said. Lifestyle and behaviour changes are part of it. The choices that we make now will determine the level of future risk. Full decarbonisation of the energy system will be required. I'm glad to see ESB are here and speaking. We'll have to do the adaptation to reduce the adverse impacts, and a risk-based approach, looking at the various risks associated with future scenarios, will be key to that. The first step will be, in terms of looking at adaptation, is to address current vulnerability and exposure, and we have a lot of DPS fund a lot of work in that area. Ambitious mitigation is affordable. The IPCC says it will reduce growth by about 0.06% on BAU, which BAU will be about 1.6 to 3% annually. And this translates into delayed, not foregone growth. And those costs that IPCC have produced don't account for the benefits. And the benefits are multiple in terms of security of energy, better, healthier society, healthier cities, healthier rural situations. And unmitigated climate change will create increasing risks for economic growth as well. So, how do we address this? The IPCC has said that to keep below 2 degrees, we have to reduce emissions between 40 to 70% relative to 2010 levels by 2050 and be near and below zero by 2100. The 40% is a bit, you have to be very careful of that 40% because it's really, some of the models that are used rely a lot on negative emissions, carbon dioxide removal technology, which would be biomass coupled with carbon capture and storage. So some of those would have major, if you're at 40% in 2050, that would require major negative emissions by in the second half of the century at a scale probably equal to the emissions we now have of CO2. So whether that is feasible or not is debatable. So back to the key messages. Climate change is happening. We're driving it. The more we emit, the more we'll disrupt our climate system, create bigger risks, and move away from a sustainable future. Technologies are central to what we need to do, and that's why this meeting is important for us and the wider community. So thank you very much.
Thank you very much.